Welcome back, everybody. Today, we're going to be continuing our discussion about reversible computing. So if you recall what we talked about last time, we discussed a alternative kind of way of thinking about classical computing that is closer to quantum computing than a standard Boolean circuit model that we were thinking about. The basic idea behind reversible computing is actually pretty straightforward. The idea basically behind it is that we require that for every gate that we have inside our gate library that maps X to Y, we require that this gate G is invertible. So in particular, if we have Y is equal to G of X, we require that there exists a operation G inverse such that G inverse of Y is equal to X. Now, this doesn't generically happen. Quite a few transformations that naturally end up occurring aren't reversible. The standard one that we looked at last time was AND. So, AND has the property that AND AB is equal to A times B. This will be uninvertible if A dot B is equal to 0. So as a result, we had to generalize this, or we had to cheat in a particular way. And the way that we cheated was by using this idea that we can store extra information or keep extra information along for the ride while we're doing a reversible calculation, and store in order for us to make sure that the result can always be inverted. And so for the example that we spent a lot of time looking at in the first lecture was the Toffoli gate, which is sort of the reversible analog of the AND gate. And the idea behind this was what it would do is it would output A, B, and, well, 0 exclusive or A dot B on this wire. And so that is the basic way that we can end up thinking about how to deal with AND in a reversible setting. And in general, we can do the exact same trick in order for any irreversible function to represent it reversibly at the price of having a couple of extra more bits of memory around in order to be able to invert the function. So that's the high level of what we talked about last time. Now, let's introduce a new notation for describing all of this. And this notation, it's going to seem kind of pointless at first, but once we start going into probabilistic reversible computing, it's actually going to end up being very natural. And so this notation is actually a linear algebraic notation. And what this notation allows us to do is this allows us to describe actually all of ordinary computing, or classical computing as we're wont to call it, as in terms of the language of linear algebra. So let me give a little bit of an example. So we had before, we had our bit strings in particular. All of these would be in Z2n normally. So, like, for example, we would have, 0, 1, 0, 0, 1 as a particular bit string. And we could think about this as just, the inside the Cartesian product of 5 individual bit spaces. So this is the sort of space that we're taking a look at. Now, we can actually come up with a different language to describe this. We can take advantage of the fact that we can expand this out to end up mapping this directly to Z2 to the n. And the way that we do this is we create a bijection between these two spaces. And the simplest way to create such a bijection is to say, take this vector over here of bits, right? And we can actually take a look at this and say, well, okay, well, what value does this correspond to? Well, we can read this in binary in order to be able to encode it as a decimal number. So for example, this will be 1 plus 0 2s plus 0 4s plus 1 8. So this would be 8 plus 1 equals 9. Okay, so we would refer to this as E9. And so what do I mean by E9? What I mean is this is this would be the ninth basis vector. So as a particular example, this would be 0, 0, 0, 0. Maybe I should have picked something a little bit smaller, but this would be E9. There would be 9 zeros, 9 zeros coming before it, and this in the 10th spot. So this is an example also, if you've seen these sorts of things before, this is an example of a one-hot unary encoding. If that name doesn't ring a bell to you, don't worry about it. This is basically just like counting in Roman numerals effectively. So for every number that we have in our space, there would be a different position of the 1 in all of this. So as an example, let's say I wanted to represent the bit string 0, 0, this time in 2 qubits, so it won't take me as long to write it. 0, 0 in 2 qubits would be 1, 0, 0, 0. 0, 1 would be 0, 1, 0, 0, and so on and so forth. So you can see this allows us to associate a unit vector for every bit string that we're taking a look at. Now, of course, we don't use this in practice in ordinary computing for a good reason. It's because of the fact that this representation requires exponential memory. In particular, if this is n bits that we're taking a look at, then the length of this vector is 2 to the n. So it's far less compact than the binary representations that we normally use. So that's one of the reasons why this language doesn't get that much play. However, innately, probability distributions are on exponentially large spaces, as in, like, if we consider the number of different possible configurations 2 bits could be in, we could have 0, 0, 0, 1, 1, 0, and 1, 1. Here, there's 2 to the 2 different possibilities that we would have to track in a probability distribution. And so for that reason, this language will start to become actually not so wasteful in settings where we have to directly keep track of exponentially many configurations to discuss a probabilistic mixture of bits. Okay, so this is the linear algebraic language for describing it. Now, this process that I mentioned for associating every bit string with a unit vector, there's actually some really elegant ways that this can actually get built or bootstrapped off of the fundamental binary representation. So let me just give you an example, right? So let's go back to everybody's favorite example. Say we've got the bit string 0, 0, right? This we would represent as a unit vector inside our linear algebraic language as this. Okay, now this, of course, we could end up writing as E00 if we feel like. But another way we can deal with this is to deal with the properties of a special type of product. And this special product is known as the tensor product. Now, technically speaking, the tensor product is a product on linear operators. But here, the way I'm going to be describing it is technically the way that one would think about the Kronecker product, which is defined on matrices, which are, of course, just a representation of those linear operators. But often in this field, people end up using the languages interchangeably. So I'll generically be calling this a tensor product, even though I'll be using it most frequently in the language of Kronecker products. So the tensor product, at least when you're thinking about it in this sense, is defined in the following way. The tensor product between two matrices, A tensor B, is equal to a block matrix. And this block matrix is of the form A00B, A01B, so on and so forth, going all the way down to A2 to the n minus 1, 0B, A2 to the n minus 1, 1B, so on and so forth. Okay, so this is how the tensor product goes. Now, I want to stress something about this block notation that I'm using. So this matrix isn't a matrix of numbers. It's actually a matrix of matrices. So every matrix in here is this constant found by, in this case, A00 times the entirety of the matrix, B. And that matrix is pasted in each of these locations. And the table of numbers that you get from this is just found by kind of growing these blocks out to the full space. So formally speaking, you can see from this definition that the tensor product, if A is in C, n by n, and B is in the complex numbers, m by m, then A tensor B is in C n m by n m. So the tensor product is a way of taking the product of two matrices, which might have different sizes, and growing a larger matrix out of it. Now, the reason, if we take a look at what the tensor product ends up doing in this particular case, let's just take an easy example to show that it exactly is the right tool that we would need in order to be able to build vectors like this out of the ordinary vectors that we've talked about. So for example, we want, let's take a look at 0, 0. In tensor product language, this actually is really conveniently, turns out to be equal to E0 tensor E0. Okay, now just to see this, let's actually just expand this all out. And we end up getting that this is the tensor product between those two matrices. And that, if we expand it out, is 1 from this element over here times the vector 1, 0. And then down here, it's 0, as per this rule, times 1, 0, which, of course, as established, is 1, 0, 0. Similarly, if we wanted to do 1, 0, this would be E1 tensor E0, which is, of course, 0, 1 tensor 1, 0. And going through the exact same analysis, we end up finding that this is 0, 0, 1, 0, which, of course, is E2. So you can see that this is a really elegant way of us combining basic vectors together in order to be able to build a larger one. Similarly, if we had, say, a 3-dimensional space, or sorry, a 3-bit space, we could end up constructing a vector corresponding to the bit string 0, 0, 0 as just the tensor product between the unit vector E0 corresponding to that guy, E0 corresponding to that guy, and E0 corresponding to this over here. Okay, and the same thing ends up following, and we end up getting that it's just 1, 0 all the way down 0, just like we saw before. Okay, so this is how we can use the tensor product in order to be able to build up higher dimensional vectors. Now, the tensor product, I should mention, is such a useful concept that it's worth me spending just a little bit talking about some of the properties of the tensor product, because we're going to be using these properties of the tensor product either explicitly or implicitly throughout the remainder of the course. Okay, and so the properties, there's many properties of the tensor product, but some of some of my favorite ones are as follows. Okay, the first one is, of course, it's a linear operation. So if we have two matrices, B plus C, that are obviously the same dimension, otherwise addition doesn't make any sense. This is A tensor B plus A tensor C. Okay, so it's linear. Fantastic. The second thing is it's also associative. So what I mean by that is A tensor B tensor C is equal to A tensor B tensor C. All right, so that's really awesome. But there's some other beautiful properties to the tensor product as well. Perhaps the most useful property is actually the multiplication property. It turns out that if we've got a tensor product of different matrices and we've got another tensor product, then the product of tensor products ends up distributing over the tensor factors. So this ends up giving us AC tensor BD. Okay, and we're going to use this in order to simplify a ton of the work in when we're dealing with quantum distributions later. So those are some of the properties about it. But one kind of word of caution I want to give you with this is that A tensor B is not equal to B tensor A. And so you can see this just as a concrete example. Let's look at the trying to form the bit string 1, 0, right? This is E1 tensor E0, which ends up, as we saw before, was this guy. However, E0 tensor E1 is equal to 0, 1, 0, 0. So that is, these two are not equal to each other. So the tensor product is non-commutative. Another property that is really nice is the fact that the matrix norm over here of A tensor B, and the matrix norm that we're going to be most interested in is the induced 2 norm, which is equal to the essentially the maximum eigenvalue of the absolute value of the operator. This is the norm of A times norm of B. So these properties are really kind of awesome, and help us manipulate distributions that we describe using sums of tensor products. Okay, well, some of this might seem like it's a little bit overkill, right? Because I've only talked about building states from it. But let's consider building operators. So say we've got the following problem, right? We've got 2 bits over here, bit A and bit B. Now, what we do is we want to put them through 2 NOT gates over here. And then we'll, of course, get A NOT and B NOT out the other side. Well, how could we think about these operations from the perspective of linear algebra? Well, the way that this ends up happening is that we can imagine these inputs over here as being EA tensor EB for the 2 bits that are flying in on this side. So for example, if they were both 0, then we would have E0 tensor E0, which would be representable as this guy. But in this case, we want to use this tensor product language to kind of to its fullest. So we don't want to have to always unfold or back to matrix language when we can use the elegant properties of tensor products in order to make our lives easier. So this operation, if we take a look at it, what does it do? Well, what it does is the NOT operation will map A naught, A to A naught, and B to B naught. And obviously, if we take a look at this, this will obviously map the tensor product then to the tensor product of AB. But recall that we have this property over here. So from that property, let's take a look at what NOT tensor NOT ends up looking like. Well, NOT tensor NOT acting on EA tensor EB. This, using that distributive property, is NOT EA tensor NOT EB. That's pretty cool. So you can see that it does the distribution correctly over the two. And just say to give you an idea about what the matrix for this whole thing and would end up looking like in this linear algebraic language, this, of course, is, well, I guess first and foremost, we've got to reason about what the matrix representation of NOT is. So NOT, of course, maps E0 to E1 and E1 to E0. So if we just take a look at this truth table, we can express the operator NOT in the following way. NOT is equal to E1 E naught transpose plus E naught E1 transpose. And so, for example, if we apply NOT on E0, what we end up getting is we get, well, E1 E naught transpose E naught plus E naught E1 transpose E naught. Of course, these elements are orthogonal, right? This is E0, and E1 is this guy. So therefore, the inner product between the two here is 0. And this one, of course, is 1. So this just ends up giving us E1 as expected. So this is a cute notation that we'll sometimes use both here and in a slightly different language in quantum in order to be able to describe matrices in a purely algebraic fashion. However, we can actually just compute these outer products in order to be able to figure out the matrix. And so computing the outer products, we have E1 E naught transpose. This is equal to, of course, 0, 1 times 1, 0, which will end up giving us 0, 0, 1, 0. Now the opposite will end up giving us E0, E1 transpose is equal to 0, 1, 0, 0. Now, of course, we could figure that out directly just by noting that these two terms are the transposes of each other. So therefore, the NOT gate has a matrix representation of 0, 1, 1, 0 in this language. Also, I should mention, of course, it doesn't make much sense to talk about a matrix without talking about the basis that matrix is represented in. Here, that basis, of course, is the basis of E0 and E1. This basis over here we'll commonly call the computational basis. And this term, the computational basis, again, is going to come out a ton. So remember to write it down. It is a very important term. It's just the standard unit vectors that describe the bit configurations that we have when we look at a system. So this is how we would figure out the representation of a matrix in the computational basis. And if we wanted to figure out this 2-qubit NOT operation, well, the 2-qubit NOT operation, of course, is NOT tensor NOT. And going through it, this is just equal to 0, NOT, 1, NOT, 1, NOT, 0, NOT, which of course is just 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0. So there you have it. That is how we can end up describing operations that are parallel on multiple bits. Now, of course, not all operations necessarily would need to be of this form. That's a tensor product. A tensor product is what we use to describe independent operations that act on one or the other. Gates like the Toffoli gate or the controlled NOT gate, which is a particular case of the Toffoli gate, these operations cannot be expressed as tensor factors. So for example, a Toffoli gate is of the form 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1 expressed in this language. And try as you might, you cannot reduce this to a tensor product of elementary matrices. So that is the operations that we're interested in. The final thing that I want to mention is, okay, from this perspective, what class of matrices do all of our operations end up falling into? So again, our gates that we have, these are now going to be translated to matrices in 2 to the n by 2 to the n. Okay, and the reason why is because this is the dimension of the input. And as we established before, all reversible operations have to map 2 to the n to 2 to the n. So therefore, this is all gates need to be of this particular form. And furthermore, because it's 1 to 1 and it has to be reversible, it's actually easy to show that all reversible operations are permutation matrices. Now, permutation matrices are matrices that are a subset of what are known as unitary matrices. And permutation matrices have this property that G transpose, when we're reviewing it as a matrix, is actually equal to G inverse. Okay, so this over here is the property that we have. And of course, all of these G's, well, I mentioned it in terms of complex numbers. In this context, we're of course just mapping real to real. And all of these elements inside each G for classical computing are going to be greater than or equal to 0. In fact, they're just going to be 1 and 0. So now that we've discussed all of that, let's now go forward and generalize this just a smidge. And the way we're going to generalize this is that we're going to talk about how to apply these operations instead of just on bit strings. Instead, we're going to talk about probabilistic bits. Okay, so how do we think about probabilistic bits? So in reversible computing, we end up assuming that all of our operations end up preserving entropy. Okay, so we have preservation of entropy, meaning that the uncertainty or the amount of probability in some sense in our system can't increase or decrease through the application of a reversible gate. So the idea basically is that what we have is if we want to add randomness into our system, what we need to do is we need to put in, instead of a bit being in a definite string, right, either 0 or 1, we put in with probability P0, 0, and 1 minus P0, 1, for example. Okay, and then we can feed these in through any reversible network that we feel like some NOT gates, some Toffoli gates, what have you. Okay, so that is basically how the how this ends up working, and the way that we can end up describing this probability distribution is through a probability vector. The probability vector for the single bit, for example, is just going to be equal to P of 0, E0 plus P1, E1. And that's just a vector that keeps track of both of the probabilities of 0 and 1. Like this. And obviously, of course, we have to have that P0 plus P1 is equal to 1 in order to make it a valid probability distribution. And of course, all of these have to be greater than or equal to 0. But of course, why would you want to be looking at some crazy system where probabilities can be negative, right? So the basic idea behind this is that we have now, instead of individual basis vectors that we're manipulating, now we've got mixtures of them. The question is, well, how do we end up defining our operations on these mixtures? So the way that we define these is as follows. The way all our gates, so let G be a reversible gate. Then we can express G acting on the sum over J of Pj, Ej. And this over here is just some generic probability distribution over the bits for the entire computer. And so this reversible gate, which could be on, or could even be a gate sequence that's potentially acting on many bits, we don't necessarily know what it is, but we demand that it act as a linear operator over probability. So, particular example, let's take a look at a NOT gate. So the NOT gate, as you recall before, had a matrix representation that was of this form over here. Now we want to figure out what would happen if NOT was acting on a probability distribution. Let's call it P0, P1 over here. So if we apply NOT to P, the way we do it is just by using linearity, like we mentioned above. And so by linearity, this is just the product of P0 and P1, which of course is just P1, P0 down here. Now that's looking at it in terms of the matrix multiplication. If we wanted to use this algebraic notation rather than matrix notation, another way of looking at this would be not acting on P0, E0 plus P1, E1, and that is equal to P0, E1 plus P1, E0 by linearity. So we're applying the NOT gate on both of these. Now the question is, we might have, why linearity? Well, linearity is actually really important here because the reason why is that if this operation was nonlinear, then its action would actually depend on the probabilities that the bits are in a particular outcome. Now, if you envision the situation like, let's say, for example, you're flipping a coin, okay? The coin has some definite state to it. It's either heads or tails. When you put it through a NOT gate, it's going to get flipped to heads or tails. But in reversible computing, you're not allowed to change with your gate operations the entropy, or in turn, your certainty or knowledge about the configuration of the state. Because if you change that, you couldn't actually go back to what the state was, or i.e. the probability distribution before that. So then if that's the case, then you can't have operations that act knowing what the probability distribution is, because it doesn't have access to that. It just has a particular configuration when it goes through your circuit. And so that's the reason why we model these systems as being linear. So linearity, we're just going to take to be an axiom here. And now the last thing that I wanted to discuss about probabilistic reversible computing is, well, how to figure out what the probability is. So, okay, so if we want to figure out the probability of X for a given probability distribution, the way that we could figure that out is, of course, if we just take a look at the sum over the probability distribution, it's of the form sum over X EX, because again, it's like P0 over down to P2 to the n minus 1 for a probability distribution on n bits. So if we have this as this over here, what we want to be able to do is we want to be able to find, let's say, probability of Y, which is just the Yth component here. So what we'd like to be able to do is we'd like to be able to take this Yth element in here, report that, and zero out everything else. Now, the way we can do that is we can actually just take the probability distribution and compute the inner product of it with EY. So the probability of Y is actually just the inner product of EY and PX EX, which we can always just express as EY transpose PX EX. And there you have it. So this is how we can figure out the probability of a given configuration. If we wanted to figure out, the probability, let's say the probability that X is equal to 2 plus the probability that X is equal to 4, this would just be equal to E2 transpose PX EX plus E4 transpose PX EX. Okay, and so that's how in probabilistic computing, you can end up estimating what the probability distribution is, or formally talk about what the probability distribution is. It's found by computing the inner products of the state you have and the thing whose probability you'd like to measure. Okay, cool. So The next thing that I want to talk about, though, that's actually a subtle difference between the two, is that there's one extra operation. It's kind of trivial, but it really does need to be considered in this model. And that last thing is measurement. So measurement, this bad boy over here, is nonlinear. And it's really nonlinear. Okay, the reason why I say that is, okay, well, let's say what we want to be able to do is we want to be able to model a computation where what you do is you actually take a look at the bit strings and draw a sample from them. Okay, so that it could be equivalent to this, canonical example where you flip a coin and then you take a look at what happened to your particular sample. At that point, what happens is the probability distribution kind of collapses now down to a single value. So in that case, let's just take a look at what happens. So we've got P, which of course is equal to sum over J, Pj, Ej, when we're describing the probability distribution in linear algebraic language. What will happen is that this distribution in the computer, when you measure it, is going to end up reducing to the distribution Ej with probability Pj. Okay, so it's kind of by definition that this is true. So that's how measurement ends up working in these particular cases. However, we can of course consider less destructive forms of measurement. What we can do is we could take a look at partial measurements of individual bits. Given that I'm running low on time, I'll spare you the details about how precisely that ends up working, but you can end up figuring out what marginal probability distributions and the like are with this. But the key thing about it is that measurement here, of course, is nonlinear, and also, unlike all the rest of the gates, is also non-reversible. You can see that because once you've found what Ej is, there's no way that you can figure out what probability distribution you ended up drawing from. You can't undo that transformation, whereas all the rest of the gates that were done before your measurement can be. So this is one of the key differences. And this operation, if we call it M, has the property that M acting on some gate distribution over here, or I should say the probability distribution that we end up finding by measuring the gate acting on some initial configuration, or let's call it, I guess, P. This is equal to the distribution that you would end up getting by applying the gate and measuring P. So for example, right, let's say I flipped a coin and I ended up inverting it between heads or tails. The probability distribution that I get from inverting it after I measure it is exactly the same distribution as I would get the other way around. So that's one of the properties about it. So at a high level, this feature of measurement causing a partial collapse of our probability distribution, as we learn from the classical distribution, isn't something that seems terribly powerful. However, in the next setting that we're going to take a look at, we'll find it is. And that setting is, of course, quantum computing. And at a high level, the biggest thing that you need to know in order to be able to separate classical or probabilistic reversible computing from quantum computing is that in probabilistic reversible computing, we had that P is equal to the sum over X, Px, Ex. In quantum, we have a quantum state vector is equal to sum over X, psi x ex. However, here we have the sum over x, px is equal to 1. In quantum, we have the sum over x, psi x, absolute value squared is equal to 1. And that's it. That is the only difference between quantum and classical. Quantum uses a 2 norm and classical uses a 1 norm. In principle now, you actually understand everything you need about quantum computing. And so, but you might ask, okay, well, why am I taking the rest of the course? Especially given that the difference between ordinary computing and quantum computing is such a minor triviality. Well, we'll see as the rest of the lectures continue that the seemingly insignificant difference between quantum and classical is actually the heart of the exponential advantages that quantum computing can get for many problems. And the whole magic of quantum computing is figuring out how to use this insignificant seeming little feature in order to provide huge benefits for computation. Thanks a lot.